Hello, everyone. Have you ever wondered how a solid cube of ice melts into a puddle of water? Or how that same water, when you boil it, seems to just disappear into the air as steam? Well, it's all because of one very important factor: temperature. Today, we are going to understand the science behind how a change in temperature causes a change in the state of matter. So let's begin. Here is what we will be covering today. First, we will understand the connection between temperature and the movement of particles. Then we will observe the journey of ice as it melts into water, and then that water as it boils into steam. We'll also solve a very practical question: why do burns from steam hurt more than burns from boiling water? And finally, we will summarize all our key learning. All right, let's start with the very basics. To understand how states of matter change, we first need to understand what is happening with the tiny particles that everything is made of. Now, everything you see around you, a solid table, liquid water, the air we breathe, is made up of very, very small particles. And the most important thing to remember is that these particles are never completely still. They are always in motion. This energy that a particle has because of its motion is given a special name: kinetic energy. So what is the link between temperature and this kinetic energy? Well, it's quite simple. Temperature is nothing but a measure of the average kinetic energy of the particles. So when we heat something up, we're actually giving more energy to its particles. This makes them move or vibrate much faster. Just remember this rule: as temperature increases, kinetic energy also increases. Now that we understand this basic principle, let's see it in action. We will take a very familiar substance, ice, and we will observe what happens when it changes from its solid form into a liquid. Let us imagine a simple experiment. As you can see here, we have a beaker that is full of ice cubes. We have also placed a thermometer inside to measure the temperature. Now, let's start heating this beaker from below and observe carefully. As we begin to supply heat energy, the particles of ice absorb this energy. This, as we just learned, increases their kinetic energy. So the particles start to vibrate more and more strongly in their fixed positions within the solid structure. These vibrations become stronger and faster as the temperature rises until it reaches a very important temperature: 0 degrees Celsius, which is 273 Kelvin. At this specific temperature, something new begins to happen. The ice starts to melt and change into liquid water. This specific temperature is called the melting point. The melting point is the minimum temperature at which a solid becomes a liquid at the atmospheric pressure. For ice, this temperature is 0 degrees Celsius. Every pure solid has its own unique melting point. Now, here is a very interesting observation. If you keep watching the thermometer while the ice is melting, you will notice that the temperature does not change. It remains constant at 0 degrees Celsius until all the ice has turned into water. But we are still supplying heat, aren't we? So the question is, where is this heat energy going? The answer to this puzzle is a concept called latent heat. The word latent actually means hidden. So the heat which we are supplying is getting used up to change the state of matter. It is being used to overcome the forces of attraction between the particles of ice. This hidden heat, which changes a solid to a liquid, is known as the latent heat of fusion. Okay, so now all the ice in our beaker has melted. We now have liquid water, which is still at 0 degrees. What do you think will happen if we continue to heat this water? As we keep supplying heat, the temperature of the water will now begin to rise from 0 degrees. The particles of water gain more and more kinetic energy, and they start moving around faster and faster. Soon, they gain so much energy that they are able to overcome the forces of attraction holding them together as a liquid. This change starts to happen at another very specific temperature. For water at normal atmospheric pressure, that temperature is 100 degrees Celsius, or 373 Kelvin. At this point, the water begins to boil and change into its gaseous form, which we call steam. This temperature, 100 degrees Celsius for water, is known as the boiling point. It is the temperature at which a liquid starts boiling and changing rapidly into a gas. And now we see the same interesting thing happen again. As long as the water is boiling, the thermometer reading will stay constant at 100 degrees Celsius. The temperature will not increase until all the water has turned into steam. So, can you guess why this is happening? Yes, it is for the exact same reason as before: latent heat. The heat energy being supplied is again hidden. It is being used to change the state from liquid to gas. This hidden heat is called the latent heat of vaporization. It is the extra energy that the water particles must absorb to break free from each other and escape as a gas.
Now, understanding this concept of latent heat is very important because it has a real-world application. It explains why a burn from steam can be far more severe than a burn from boiling water, even when both are at the same temperature.
Let's look at this comparison. On one side, we have particles in boiling water at 100 degrees Celsius. They have a high amount of kinetic energy. But on the other side, we have particles of steam, which are also at 100 degrees Celsius. They have the same high kinetic energy, but they are also carrying that extra hidden energy that they absorb to become a gas, the latent heat of vaporization. And this is precisely why steam is more dangerous. When steam touches your skin, it first condenses back into liquid water. In this process, it releases that large amount of latent heat directly onto your skin. And then, the newly formed hot water at 100 degrees also releases its heat. So your skin absorbs much more energy from steam, which is why it can cause more severe burns. So, we have completed a journey from a solid to a liquid to a gas. Let us now take a moment to quickly summarize the most important points we have learned today. So, what are our key takeaways? First, temperature is simply a measure of the kinetic energy or movement of particles. Second, during a change of state, like melting or boiling, the temperature stays constant. This is because the supplied heat is being used to change the state. This hidden heat is called latent heat. We have latent heat of fusion for melting and latent heat of vaporization for boiling. And finally, because of this latent heat, particles in steam at 100 degrees have much more energy than particles in water at the same temperature. We have seen very clearly today how increasing or decreasing the temperature can change the state of matter. But temperature is not the only thing that can do this. There is another factor: pressure. What do you think would happen if we change the pressure on a substance? Well, that is a question we will explore in our next topic.